Hello, so let's set up a case. Let me show you all the steps to set up a case of an airfoil. Okay, so the first thing is important. Remember, this is the data format that you need to have, that you need to use in Ansys. Okay, it's a little bit different from the one used in Xfoil, but it's not that difficult. Okay, you just need the coordinates. Now you need to give the coordinates in 3D, you know, X, Y, Z. So you take the airfoil from Xfoil, you just put here 0, 0, 0, 0. These are groups. Remember I mentioned that you need to separate the groups in top and bottom surface. Okay, so later I will show you, but basically this is the file format. So here I already prepared the file format for me, but remember launch Ansys. So look for the Workbench. So you have here and using 2020 release 2. I hope you are using Design. Otherwise, we're going to have a slight different in the GUI, but pretty much the results will be the same. Okay, so we are inside the user interface of Workbench. So remember here, we need to drag and drop now what we want to use. So the steps is first we need geometry, then mesh, and then we run Fluent. So the first step to generate the geometry is here. So go here and drop it here. Okay, so we have the geometry, and now we can create our geometry. So you can right click here. So all the time when you see here, the question mark means that you're missing data. So you need to enter there and insert the right data. So you right click here and let's use Design Modeler. Okay, this is another software to create the solid model, but for us, it's okay to use Design Modeler. Okay, so double click there and it will launch that application. So now that we're inside Modeler, this is a CAD software. It's not a state of the art. Okay, it's not something like SolidWorks or CATIA or Uncharted, but it is a CAD software. It works fine, and this is the one that we're going to use to create our geometry. So the first thing is that we need to import those coordinates. Okay, so let me tell you something about those coordinates. So here I already have it. So I have my data. I will share the data with you also. So very important that, let me open. So you have to be careful also with your operating system, what you are using as a decimal point. Okay, so it's likely probably that you have the Italian language and your separating mark will be comma. Okay. But if you are, like in my case, I'm using points. So be careful about that, okay? It's very important. Also, as for Xfoil, do use a decent text editor. Do not use Notepad because it will give you problems, okay? So first, look at in your system, the decimal separator, comma and point. In my case, I will use point. And then, very important, here you have some comments in the file, okay? So if you want to add comments, it is the pound or hashtag or numeral, whatever you call it. And then blank lines are ignored, and this is the format that you give. Okay, so you can give the airfoil the whole loop, okay, in one single block. So see that we have one single group. So all in this case we're using 200 coordinates. Okay, what is important that when you give one single loop, you cannot close the loop. So see here that we're starting from 100. You cannot close it again with 100 because it will give you a problem. Then you need to close it manually. I will show you. The order is very important. Okay, they need to be contiguous, but it's not like in Xfoil that you start from the trailing edge and move to the leading edge and so on. So here you start from whatever you want, but the important thing is that they need to be contiguous. Okay, the coordinates. So see X, Y, Z. So group and a counter. The way I recommend you to do is to separate it in 2 or 3 or 4 groups, or as many groups you want. So in this case, see that we have group 1 that will be top surface. So see the counter here, 1, and then when you are going to add the bottom surface, okay, change this counter and you put the coordinates there. So now when you put it in this way, you can close your loop, okay? There is no problem that you have the same coordinates as the one here because we have different curves separated. Okay, I will show you the difference, but this is the way I recommend you, okay? You can have many groups, okay? But usually airfoils 2 groups are okay, top and bottom. So to import these coordinates, you go here and concept 3D curve. Okay, so here this is the, let's call the canvas that we have in Design Modeler. Okay, so you have all the options here. So probably if you are familiar with CAD software, kind of similar options. I'm not going to go into details, just to show you the basic to import your geometry and do your mesh and the simulation. So you're going to concept 3D curve. And see here that you have the 3D curve. See that you have a light in there. Means that when you have a lighting, you need to update that. Okay, so to update that, here you have the generate button. Okay, but before updating that, you need to read the file. So see here that you go here in the button, you have details view, you click there, and you have different options here. Okay, so we want from coordinate file. Then click here, the ellipses here, and then locate the file. Okay, whatever you have it, look for the file. So in my case, I go here, and I should have it here, 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 and you open your file. So I'm going to open first the one that we have one single loop, B0, open. And now that you have the file, see, you can say also in the plane that you want to project it. Here also operation, I recommend you always add here, add frozen, okay? Generate. And now here you see that you have something there, but you can here fit to screen. So see here that you have shoot to fit, zoom to fit, then make it normal, and you have it there. Okay, so this is your airfoil. And what I was telling you that there you have a single loop. So what is remember that when we were plotting in airfoil or XFLR5, sometimes you can split between open and you can split now the data between top and bottom surface. Okay, suction pressure and suction side. Here you cannot do it because you have one single surface. So it's a good idea to do that the same plotting. Okay. But there is no difference in the solution. The same is that how you handle post-processing data. So probably you're going to have this axis here, now in the curve. So here you have many options, you can play with them, but just to show this, that sometimes can give you some problems, you can come here and deselect this one, cross-section alignment, and also go into view and select here display vertices, and it will show you the vertices that you have in this single loop, in this single curve. So here you have the wheel, okay, of your mouse, control middle button also to pan, okay, but also you can click here, choose the option, or you move with your mouse, so just play around, you will get. But let's zoom here, see here that you have this, and it's a small gap there, so it's not close. So you can imagine that because here you are creating kind of a spline, so if you close it, it will give you an error, so that's why you cannot do it. Okay, so when you import here, it will give you an error, so do not close one single curve. So if you choose to work in this way, now you can close it manually. To close it manually, just come here, concept, and you have lines from points. The points are those two you see there. So click here, and now you can select the points. Okay, so you click this one, press Ctrl because you need to select 2 points, and see that you have the line here, see that you have the light in there. Okay, here again, operation, you can use add material or add frozen. Remember, I recommend you always to add frozen there, generate, and see that now you have there, it is closed, the new line. So now that you have this, okay, these are just lines. We work in surfaces, so we need to create a surface from these lines. So to create a surface from these lines, you go in again to concept, and you press here surfaces from edges. Okay, so now you choose the edges. So I will do, you can select manually Control on the edges, or you can do Control A, and it will select everything. So apply here, so you see that selected to curve, generate, and now see that you have a surface. So you generate a surface from those lines. Okay, so see here that you have all the parts that you have in your solid design or surface design. So see that these are the lines that you created, and these lines from the moment we don't need them. So you can select there, right click, and suppress. And now you have this single surface. Okay, so you can zoom in, zoom out. Okay, and you can get now an idea what we're doing. So you have this surface, then you have the outer domain, and then you are going to do a Boolean and you subtract this surface from the other to have that domain. So this is how we work. So now let me show you the difference with the other. Okay, so see that we have this one. I don't want to see this one, or I don't want to use it later, so I will suppress everything from my my design. So now let's import the other ASCII file where we have the coordinates. So you go again here, 3D curve, from coordinate files, select the other one. So see here that you have also Unix, the plane, so it's play around with those options or change it if you want. Add frozen, generate, and we have this. So now you see here that when we import it, see that now we have two lines, and see that that will be upper and bottom, top and bottom side. So now you can do a better post-processing and computing quantities. But see also that you have the vertices, but everything is a closed loop, okay? You need to do any work manually. So this is the advantage of separating the curve in groups. That is the way I do it. I recommend you to do it like this. Not necessarily needs to be two. If you want to have more than two, it's up to you, okay? So probably you can separate it here in the quarter line, it's up to you. But usually it's okay like this in airfoils. So now we do the same as we did previously. Okay, so you go concept here, surface for edges. So I will select now manually, Control, apply, generate, and now you have that new surface. So see that you have your lines there. Let me suppress, because from now on I don't need those lines. I just need the surface. And see that you have exactly the surfaces. Let me unsuppress this one. Now right click on suppress body, and see that these two are exactly the same. The difference is the input file, okay? But if I suppress this one, okay, see that in this one, if you select the edge, you are selecting the whole loop, okay? So see, attention, if you want to set here, you have selections. So for instance, you want to select a surface there. So you want to select a volume or an edge, you click there, okay? Or a vertex, you click there. Okay, so you can choose what you want to select. I want to select an edge, click there, and see that you are selecting the whole, let's say, loop. But now as you go to the other surface, see that you are selecting upper and bottom side. So you have more control. So work in that way. So now that we have this, we need to create the external domain. Okay, so remember that we're working in this plane, XY. So here you select here, and now we need to add a sketch here. So to add a sketch will be a rectangle or whatever you want to add. I will add a rectangle. Click here, new sketch. Okay, now you enter the sketching actions here, and you can start to draw. Okay, so let me draw a rectangle. So I don't need to give dimensions initially. Then I can control that, but see that this is my outer box. So here you see that what we're going to do in the CFD simulations, now we have, this will be a boundary, okay? So here we are going to have flow entering here, going out here, top and bottom walls or outlets, whatever, and then walls around the airfoil, okay? So now we need to give boundary conditions, okay? So something that we haven't done previously in potential methods. Now here we need to do it in CFD. Okay, but we need to create the outer box. This is a general guidance, okay? Because this is another question, okay, beginners ask. How small or how big needs to be this? In external aerodynamics, and working in this, like in this case, is large Reynolds numbers that we're going to do. Usually it's a good practice to put it 10 times the core, okay, in front, top, bottom, and 20 times behind, okay? So why we need such a big box? Because we don't want to have, you know that here you're going to have a pressure, okay, evolution here. So we don't have well, and also a velocity gradient. So we don't want to have a strong gradients close to the boundary, because that can affect the stability of the solution. So you need to put that far away in such a way that you don't have strong gradients. Okay, so now to give dimensions, to move here, see here that now you have dimensions tab here, and we can add dimensions. So let's add horizontal dimension. So you select this line, and we want to give this dimension reference with this one. Put it there, and do the same here. Okay, put it here. And do the same here, vertical, okay, middle line, Okay, bottom, middle line, you have it there. So see that you have H1, H2, B3, B4, you have it here. So now you can give the right value. So for this one, let's give 10, 10, 10, and 20. So fit soon. Okay, now, okay, here, okay, let me, and see that you have your box. So here from sketching, we are done in sketching, modeling, okay, and see that this is what we have, our box. So here is very intuitive. You see that it's quite different. Even if you have shockwave, that shockwave here, it won't interact with this top boundary here. So this is the ideal choosing your external domain. So now that we have this, what we need to do from this sketch, we need to create a surface, okay, and then we're going to use this airfoil to create a boolean and have the surface with a hole, okay, using this one, okay. So we're going to create a subtraction. So to create a surface using this sketch, you select this sketch, you go into concept here again, and see here that you have this option, surfaces from the sketches, okay. So okay, select the sketch, apply, always use here add frozen, okay, and now you see the lighting there, generate, and now you have your surface. Okay, so see here that now you have surface 1 and surface 2, your airfoil. So now what we're going to do is a boolean, subtract this one from the other one, and you have your surface, and now you can create the mesh. A few things here, so see that here you can rename this. So see that you select this one, and you can call it here, I don't know, if you want to change the name, airfoil, and you can create this one, you can name it now, domain. So this is optional if you want to change the name just to recognize better now the surfaces and see what you're doing. Also optional here you have this action fluid solid, so you can select a fluid. So this is not compulsory, but if you put fluid, if you are going to do a CFD simulation, you put fluid there, it will choose some default parameters, and you need to do less clips, no less selections, okay, but it's not compulsory. But yeah, I usually put it all the time, fluid. So now that you have these two, we need the next step is just to create that boolean. So as you go here into create now, see here that you have boolean. So what we want to do, you have different actions, unite, subtract, intersect, imprint faces. So I want to do a subtraction. My target body will be this. And my tool, the one that I'm going to use to cut the hole here. So see that you have two bodies there, but you are not selecting the airfoil. If you want to select the airfoil, you can go here and select the airfoil, but also you can do the selection from here, from this tree. It's up to you how you do that selection. So that you have this, generate, and see that now you have this surface with the hole. You zoom in and see that if I select the lines, still I have the lines, okay, like this top and bottom surface. So now we're getting there, the geometry. So this is a valid geometry, okay, but one thing that we need to do also, that probably I will ask you to run 3 simulations at different angle of attack. Okay, but you see that then we have another option just to rotate this one. Okay, so this can be done parametric. So let's add the option to do the rotation of the geometry. So see here that we did the boolean here. Okay, but we need to do that rotation, let's say, before doing the boolean. So to do that, I will right click here, insert, and then you add body transformation. And see that you have many operations. I want to do a rotation. So what you want to rotate, select the body. So see that you do it before the boolean, because after it doesn't exist anymore, that body. You select the surface, apply, then axis definition. So you choose an axis. So I will give components here, 0, 0, 1. So it's the axis normal to your screen. This is the axis. So see that here you have this sketch that's showing you how is the rotation done. So it is okay. And here you give the angle. So in my case, you give negative angle to go down. So for instance, you want now to rotate to the simulation -10, you just insert the value here, generate, and see that everything is done automatically, okay? So now you have something that is parametric, Okay, very handy. Okay, there are many ways also to do parameterization. I'm just showing you one way, but there are many ways to do parametrical study and to add automation in your simulations. Okay, so in the end, at the end of the day, you would like to run, let's say, hundreds of simulations. You don't need to do this manually. Okay, you just define what are your parameter variables, and then somewhere in the Workbench you will define how many experiments you want to run, and then Ansys will do it automatically. Okay, so now that we have this, okay, this is a valid domain, we can do the meshing, but now let's start to think about the solution, okay, because we know that we have the flow, and let me rotate it, okay, so let me rotate it 4 degrees. So I put it here, so you can imagine that you have the flow coming here, and then there is some separation here, and there is a wake behind this airfoil. So it might be a good idea to add a region here where we add more cells, okay, to control the cells concentration. So that is something called body of influence. So let's add that region. So that is another sketch. Okay, so you go here, new sketch, you have the sketch here, and then you create that region. Can be a circular region, can be a rectangle, it's up to you. In my case, I will add a rectangle like this. Okay, so you create this box, not necessarily needs to be the same, exactly the same dimensions as the other sketch, can be larger, okay, it doesn't matter. Okay, so in this case, we have this one, and what we're going to do is inside this box, I will put more cells. Okay, I have more local control. Again, we can add dimensions. So I will put here, so usually here what you do is 2 times the core, so 2 times front, 2 times top and bottom. Okay. 2 times there and 2 times here. Okay, so this is your box. And here, then when we do the mesh, we're going to see how we're going to do that. We're going to add more cells in that region within that surface. So now we need also to convert this sketch into a surface from sketches. Select the sketch, apply, add frozen, generate, and you have it there. Okay, so I think at this point we are done. Okay, we have done all this definition. So if you want to do if you want to add multiple body of influence, it is okay. Or if you want to do a subtraction, you know how to do it. Okay. One thing also, remember that forces are parallel or perpendicular to the incoming flow. So in this setup that I'm doing, okay, I am rotating the airfoil. So my velocity, incoming velocity, is always in horizontal, no, in the X direction. But also you can leave the airfoil fixed, and then you can change the incoming velocity. Okay, however, this domain is not ideal if you change the incoming velocity, because you need to add also boundary conditions here and here. Okay, so usually probably you have seen like circular domains or C-type domains. That is when you decide to do that. But I like to work like this. There is no difference. Some cases rarely you need to do different geometries and take different consideration. There is no difference. I like to work like this. Okay, so in my case, I always will have velocity aligned with the X direction, and then I will rotate the geometry, but we have seen that everything is parametrical. Okay, so we're done here, and we can close this. Okay, so let's close this. So you have the geometry, and also remember to save every now and then the project. So you go here, File, Save As, and save it whatever you have it. So I'm working here, example, I would call it case 1. Okay, so you save the project, and it's very important, okay, because you are going to have a data structure. Okay, so here in Files, see that you have the location of all your files. Maybe you don't see this. If you want to see this or hide that, you go here in View, and you can choose what you want to see. So see Files. If you don't see Files, you go View, select Files. And you have also more options here. You have errors or messages. Okay, you can enable that here. Okay, but always put the files, and remember that you're going to have all these files here. So here, this is the geometry, then we're going to have the mesh, then the fluent cases. So always pay attention to this, because here sometimes you can have a lot of files that can take a lot of space, that sometimes it's a good idea to do some cleaning. So in my case, I'm putting everything here. Okay, so see that this is the data structure in Workbench, and all the files are put there. Okay, so you have all the location there. So now we need to generate the mesh. So see that you have here the green check mark, means that the mesh is okay, or the geometry is okay. So now we can add the mesh. Go here, drop it there. Now see, this means that requires refresh. Double click, it will read the geometry, put it here, and then it will open the meshing tool. Okay, so in doing this, when it's creating a new file, that probably you are going to see here. Okay, so it's always a good idea to know where you have your files. Okay, so this is the Ansys meshing. So there are different meshing tools in the Workbench. Now we're going to use this one that I think is the easiest one. Okay, so this is what you have. So you can orient there. So see that you have this. Whatever you created in the geometry, you see here. But here now we're going to do the mesh. So see that also you are taking the same names that you are creating there. Okay, so this one you call it domain. This one I didn't change. I forgot to change the name, but you change it. Okay. So one thing that here you see the color, this one is transparent, this one is solid. So this is related to the fluid option. So this is something for visibility. Now, so as you put it fluid, it will be transparent. This one by default it was a solid, so it's a solid. So that's why I like to change it, but it's not a problem. You can also change the color here. So if you click here, you go graphic properties and then transparency, you put it there. Okay, so it's not a big of a deal. So now that you have here, you can create a mesh. So you click here, mesh, and here you have all the options. Okay, something very important that you need to choose the right physics preferences here. So see that here is mechanical. We don't want to use mechanical. We want to use CFD. So choose CFD and it will choose parameters for CFD. And what you see here, these are global parameters. Okay, so you have your solver preference. So you can use Fluent, CFX, bullet flow. In our case, we're going to stick with Fluent. Okay, and element size that you see here, this is the global parameter. Okay, so the maximum size of the element would be 1.9 meters, so it's rather big. Now, remember our core is 1, so put 1 there, the largest element would be 1. So as you move your cursor into your canvas, see there that circle there represents the maximum element. So you have that visual reference, okay? So as you put there 0.5, now you have a visual reference of that element. Okay, so I will leave it 0.5, and then you have here this option sizing. So this is also to control the refinement according to gaps or curvature. So see here that we have some curvature. So here you have those options. So you want to capture curvature. So this by default is yes, and this is the minimum size when you have curvature. Okay, so when you have large curvature, put elements of this dimension. So as you keep zooming, see these other circles there represents that dimension. So see that I would change this one to 0.1. See that now this is the curvature. So if you want to resolve the curvature, you should put something. I would put in my case 0.01. And that will be the dimension. Still is a little bit, the smallest circle that you see there correspond to the feature size. So something important that is, if I put here 0.01, it will give me this warning, because the feature size needs to be at least the same value or smaller than the curvature. So if you put it here like this, now it's okay. So see that now your smallest element will be like this, which probably is a little bit slow, so small. Let me put like this for the moment, and see that that will be the smallest element size. Okay, and then you give this angle. These angles, you put it a smaller value, means that it will add more curvature, more elements where you have more curvature. Okay, you have a very good help, by the way, here. So press help and it will give you more information about this. But what I'm giving you are kind of the recipe that you will use for the moment. So see that we define those parameters global and curvature. Those are not global, but now we can go also locally. So we know that we have vertex here and we have a curve, so we can add local refinement also. But before doing that, let's generate the mesh and see what is going on. So now see that you have the lighting there, and here you will have different options, okay? Automation, selection, display. Go into mesh and see here that you have generate. Press there, generate, and it will create a mesh. Okay, so see, this is what we have. So see that what is happening here is doing a quad mesh. Okay, there are different methods. So see that is using in, see that where you have more curvature is putting more elements, as we did know, that was controlled using the global options. But see that what is happening here, that we chose also, we wanted to use this external rectangle to control the refinement in that region, but see that it's doing two meshes. So now we need to tell Ansys Mesher that this external, but this one is used to do a body of influence. Okay, so we need to add now local refinements. Okay. By the way, probably here when you select something, it will give you information. So in my case, probably for you will be message. So here you can choose what you want to see. Okay, here I'm choosing this selection information. So you go here, right click, and see here that you have options to insert new local refinement. So let's insert here. First, let me insert sizing. Okay, so let's insert a NACA sizing, and I want here, okay, element size instead. Okay, let me erase it. Okay, just let me follow first. Let me delete. Okay. Okay, so now I delete that. Okay, so here it's telling you that this measures select whatever. So now let's do it. Okay, so insert, and first I see that you have a method here. So first let's insert a method, and you can select where you want to put it. Okay, I want to put it here. Okay, select, and here you have different actions. So see that you can have quad meshes, triangles, or multi-zone. So I recommend you to use triangular meshes. So put triangles, and now next let's generate. So see that it's going to generate now triangular here, and this one is still quad because it's default. Okay, but see that you have many control in your mesh, even in the element type. So now let's define a refinement zone using this rectangle. To define that, you go again here, insert, and you go sizing, and here in the option type, see that you have body of influence. Select this one. So you have an option now that will tell you scoping method. Where do you want to apply that refinement? I want to apply it here, and I want to use as a body of influence this geometry. Okay, and inside this geometry, I want this dimension. So if I zoom in again, see the circle, it will give you a reference. Okay, so if I put here 0.1, see that the elements there will be about that size. So let me put 0.2. Okay, as you press now generate, you have this. Okay, so see that now you don't see that the surface, okay, now it's being used just to add that refinement. Okay, and we're getting there. Okay, so now you get an idea. There are boundaries here, you need to give values, you create your refinement, but now we can add also refinement in the surface. So remember, in the airfoil you have a boundary layer. Okay, you need to resolve the boundary layer, and the boundary layer is a very thin region. So with this element side, we are not resolving the boundary layer, but also if you have vortex shedding or some structures here detached and separating, you are not resolving those structures with these elements. Okay, a lot of these length metrics are related to turbulence modeling, so then there is a course related to that, and you are going to understand better all those structures. But your mesh is strongly related to turbulence, and turbulence in CFD is the most important thing. So far in the potential methods, turbulence doesn't enter. Okay, here in CFD you need to define, and there are many models. So let's add some refinement in the edges. So remember, here in the selections, see that you can select the edges, how you create it in the geometry. So as you go here, you can add sizing, And you can imagine that you select the edges, these two, and now you can add the size in there. Okay, so apply, see the two edges, and now here you see this yellow element there means the element size. So that is rather high. So here you can change that one. So if you put 0.1, you get something like this. So now you have there your visual reference. So let me put 0.01 and you will get that. So again, this will be another kind of standard practice. How many elements you put in the airfoil? So usually you are going to take your core. Okay, in this case we have our core, and it's a good practice to put about, let's say, 50 elements, okay, in your surface, okay, at least. Okay, so you see here that you can give element size, but also you can give numbers divisions. Okay, so it's up to you. So as you put 100, okay, so this will be like 50 up and bottom, so at least. Okay, so it's up to you. Okay, so you can go 200. Okay, but in our case, and working with a unit airfoil, let's say let's put something about 0.05. Okay, that it will be something about 100 elements in the surface. Okay, so now if I go here, generate, see that now we have this local control. Okay, so now this looks much better. Okay, so now you are resolving, okay, better curvature, but all these structures that will be around the airfoil. But still, remember that we have a boundary layer here, which is a very narrow region, very thin layer, and these elements, they are not good enough, or they are not small enough to resolve that. So now we need to add another type of element to resolve that. Okay, so as you go here, insert, you have this option, inflation. Okay, so this is in a specific mesh element type to resolve boundary layer. So you go inflation. So it will ask you, where do you want to create the inflation? I want to create it in this region, and you want to grow that inflation layer from what boundaries? Okay, so here, boundary, you go and you select the edges or surfaces if you are in 3D, apply, and now here you choose how many layers you want. Let's put 10. Okay, put here 10. As you press generate, this is what you have. Okay, so now I hope you understand better. So see that now you have this prismatic layer that resolves the boundary layer. Okay, so now this is a good mesh to resolve the boundary layer. There is a lot of theory here about how small this element needs to be, okay, because we can have an estimation of the boundary layer of this length from the surface to the cell center. Okay, so to resolve the boundary layer. Okay, so here I will give you a guideline. Okay, so for us, that is related to Y+. So as you go to internet, as you look like Y+ calculator, so as you go there, you will find, so probably you're going to find this one by point wise. Okay, there are many of them available. So the theory is relatively simple behind that one. Later in tolerance we can check that. Okay, I won't address the theory, but basically what you give here, you're going to give the reference velocity. So for us now, we need to give that reference velocity. Okay, and let's say that we want to work with a Reynolds number. Okay, so let me go from scratch because there I already have values. Okay, so probably you start from scratch and you get here. So you give velocity here. Okay, you give your viscosity properties, reference length. This is to compute Reynolds number, and a reference Y+ value. Okay, I will talk about this later. Okay, so compute. So see that this is our Reynolds. So I want to work with something about 6 million. So our velocity will be 90. Let's work at density, viscosity, at sea level, no compressibility effects. So this is okay for velocity, and this is my reference length. And the Y+, this value means that if you choose a value close to 1, means that you are resolving the boundary layer. Okay, you are capturing very well the viscous sublayer. Probably you saw that already in the boundary layer theory part of the aerodynamic course. And then is you choose the Y plus to values about 60. Okay, you are still resolving there, but now you can use, okay, larger cells close to the body. So see this distance, okay, from the surface to the first cell center is this distance. Okay, so you go to the calculator, is this one. So as you go 1, you will see that you will need to have very, very small cells close to the surface. And as you use 60 or 100, let's say, you can have larger values. Okay, so there is another theory, there are models behind that. For our case, let's run using a Y plus of 100. Okay, but later you can go and generate your mesh for a value of 1. Okay, and then you run, you're going to say I will show you, but for our purposes 100 is okay. So when we generate the mesh, we need to measure, okay, this is an estimate, okay, order of magnitude, but usually it's a good estimate. But always we need to check that in the CFD results. So this is the value that we need to have. So we can measure this distance here. So as you go here, you will see that to measure, let me go into display. Now it will be mesh, and I want to do here node selection. And important here, is you are in message, move to selection information, and now you can select nodes of your cells. So select one and then control and select the second one. And see here that it's giving you the distance. Okay, so the distance between these two is about this, which is roughly, let's say, this value. Okay, so probably for us, maybe it will be something like this for a Y plus of 50. Okay, it still is okay. Important, okay, it needs to be, let's say, close to 60. In our case, it's something about that. Okay, so see that you can measure. So if you want to have it this cell closer, basically what you need to do is increase this one. So you will see that I put 20 there, and if I generate, see that now everything is closer, and now you can measure from here to here. Okay, control, and see that you have this distance that probably is closer to Y plus values around 1. For in our case, let's leave it here 10. This is the recipe how you will need to do it for your airfoil. Okay, and here you fit the screen, and this is our mesh. Okay, so see that we have the refinement region, and by the way, everything is parametric. So as you change your geometry, all these parameters that you put here remains in memory, so everything can be done automatically. You don't need to redo this. So let's use this mesh. Something important as well, always pay attention here in the tree. So in connections, if you see this question mark, means that you need to fix this. Contacts, right click and delete this. You need this, delete. Okay, and you should have everything here green check marks. Okay, just always now and then save. So here we have our mesh, but what is important also, we're missing that before going to CFD, we need to have named selections. These edges or surfaces, we need to give a name, because there we need to assign boundary conditions. So as you select this edge, right click, see this option here, create name selection. You give it a name, inlet, and you have it here. Okay, so now here you can apply your boundary conditions here. Instead, if you don't add name selection, you are going to have a single surface, so it's impossible to apply individual boundary conditions. So now let me go here, top, create name selection. I will call it top. You can also put the name selection in groups. Okay, so here I'm putting in separate, but if you want, you can put it in one single group or in separate groups. This I will call it outlet. And now you go for the airfoils, and I will call this one, okay, I will call it, let's say, P side, pressure side, and this one is side. Oops, it's different now. This should be pressure. Okay, so If you want to change the name or you want to erase it, just delete or rename. So you have many options there. So I want to rename. So this should be PSI and this should be rename. Okay, so SP, okay, and then you have the other. So this is very important, okay? Remember, you need it for the boundary conditions, okay? So now that we have all the boundary conditions, all these surfaces or edges, lines where we're going to apply boundary conditions, we can move to Fluent. So if I close there, remember to save everything. So now look at here are your files. So see that now you have this new file that corresponds, this is the mesh. Okay, in Ansys Mechanical, now we need to convert this mesh to Fluent or to transfer the mesh to Fluent. To do that, you select your solver, Fluent, put it here. See the lighting means that you need to update that. Update. So what it's doing while it is updating is just converting the mesh from this format to the format that Fluent likes. The same will be if you use CFX or any other solver. We'll convert this format to the format that that solver will take. So checkmark has been converted. This one means that you need to define the case. So you double click, you open Fluent. So but see here that now you have a new file. This is the Fluent mesh. So now let's enter into Fluent. So double click, and here just take default options, okay? But here usually you can work in parallel. So parallel means that you are using more processors, it will run faster the simulation. So in my case I have 4 processors, 4 cores. I can increase it. Today's computer, most of the laptops comes with 2, put 2, but 1 is also okay. These are small cases, so it shouldn't be much different. But I would put 4 cores, okay? GPU, leave it to 0. Then press start. And it will launch Fluent. Remember, here you have the location of all the files. Okay, so you go whatever you have that case, then you can explore. Okay, let's wait for Fluent. Okay, so it's launching in Fluent. Sometimes it will give you some warnings there. Don't pay attention. This is just a warning. Okay, it will read the mesh, everything. But while it's doing that, here you go here. See that DP0, and you have all the files. Flu will be Fluent, and here you have the mesh, the set, everything. Okay, so if you want to know the locations here, okay. So in our case, see that we read the mesh. Okay, exactly the definition that we did in the geometry mesh you are seeing here. Okay, so now we can set up the case. Again, I will give you the workflow to run for airfoils, but this is very, very complex. Okay, it's not like using Xfoil or potential solvers that you just read the geometry and go. Here you need to give a lot of actions. So there are 2 ways to work in Fluent. You can use the ribbon here that you have all the options here, or not all, the most important options. There are many more things that are not exposed to the user or to the average user. And then you have this vertical outline workflow. I like to use this vertical tree. Okay, so you start to click from the top to bottom and you start to define your case. But the first things that you need to do, and this is a standard practice, always when you read your mesh, it's always a good idea to check the mesh quality. So you see here mesh quality, press evaluate mesh quality, and it will evaluate the mesh quality and it will give you some information. So for 2D cases, it will give you this warning here that, okay, your minimum non-orthogonal quality is not okay. This is a warning, okay? So you can try to fix that, okay? Or you can work not paying attention to that. Fluent is a very robust solver, so it will work okay. But if you want to fix this, you have the option to automatically improve the quality. So if you want to improve the quality of the mesh, again, go back here, and here you have improve mesh quality. Press improve, and Fluent will do some refinement, smoothing, and it will try to to improve the mesh quality. So as you go back here, evaluate mesh quality, see that now you don't have that warning, okay? Not necessarily when you do that one will fix the problems, but it works, sometimes doesn't, but it's a good standard to do it, okay? But if in your case, when you get the mesh and you get this warning, don't panic, okay? Ensure that Fluent will work, or at least don't get values in the order of 10 to the minus 6, okay? Because that one maybe will give you a problem. But if you have something 10 to the minus 5, 4, 3, it is okay. So now that we check mesh quality, we start to work here in our vertical tree. So the first thing is that you keep you click in general, and here you start to choose now what type of solver. So see that the theory here is very complex. So in our case, we're going to work for the moment, or for this external aerodynamic case, use pressure base, steady solver, 2D planner here, and that's all, okay? Then we move to models. So here is where things get complicated, because here you can enable all the models that you have in CFD. Everything that you can couple with your fluid dynamics equation, you can enable here. So as you see, things can get very more complicated. So for us, we're going just to focus in this viscous. This is related to turbulence modeling. As I mentioned, it's very important in CFD. So take the default option. So see that here you have many models. There is not enough time to address this one. This is one semester course just to address what is the meaning of that one. But take the default option, which will be the K omega SSC. Then do not select anything else, okay? Again, you have a very good help. So if you press help somewhere, you will have it here. You can see what is going on there. But these are just model different. You can enable energy equation, multi-phase flows, heat exchange, species, combustion, acoustic structure. So see here also electrical potential. So this is a very complete multi-physics solver. Then you go into materials. So here you choose your working material, okay? So in our case, you go fluid. And by default, Fluent choose air, which is okay. And here again, you can enable models. So see that you can have ideal gas, whatever. So for us, in our case, constant density, constant viscosity. Again, you can choose different models. But for us, this is okay. And you have different working fluids, okay? You have a database, so it can be very complicated. So leave it air, okay? Now we move to cell zone conditions. So one important thing that here you can set operating conditions. So as you click here, you can define your reference pressure. Okay, so you can tell you're working at sea level or pressurized environment or at 200 meters, whatever. Okay, so you choose your reference pressure. You can enable gravity. Okay, in our case, we don't need it. So let's use the standard sea level. Okay, and also, for instance, you can go also here in domain, and these are more advanced options to add source terms. For us, we're not interested in this, but as you see, it's very complicated. Okay, CFD is not like the potential flow. Okay, now you go boundary conditions. Okay, so here you define your boundary conditions. This is something that we haven't done in the potential solvers. Now CFD, you need to do it. So if you click here, and remember, these names that you see here are exactly the same name selections that you create in when you were generating the mesh. Okay, so this is important. You need to create it because you need to tell Fluent what is entering, what is going out, what is happening as the wall. So as you go here, you select inlet, that you know is this one here. You can choose the type. So see that you have many types. For us, the inlet will be a velocity inlet. You press edit or you select here, you can give the values. So see here that you can give your velocity. For us, we say that it's 90 for that range of 6 million. Okay, and nothing else. So leave these options, default values are okay. You close, then you go to outlet, which is this here. This is a pressure outlet. It is okay, but press edit. And here you can give the reference values. Okay, use the default values that are okay. So attention that this is a relative pressure. It's relative to the working pressure. Okay, so you can give absolute or pressure or relative values. Okay, but this in this case is relative. That's why it is 0, because it's relative to the working one. See, if you put the operating pressure to 0 here, then you need to put this or whatever value, but do not put 0 in both, because you are going to break this solver. You are working in Bakun. Navier-Stokes equation are not valid in the Bakun. So be careful with that, but in our case here, 0. And then you can close, and then you have bottom, this one, top and bottom. Okay, so this you can put also as a pressure outlet, but it tends to be a little bit unstable, so it's better to put this a wall, but a wall with no boundary layer. So how do we do that? So see that here by default is a wall, but it's a wall where you have boundary layer. So we want to disable the boundary layer. So to disable one, you go here, specify shear, put 0, 0, and then you have a slip wall, basically, no boundary layer. You do the same for the top. Disable. Okay, so we have done inlet, outlet, top and bottom, and now we have the airfoil. Okay, so in the airfoil is a wall, but in that wall we want boundary layer. Okay, so you leave that as it is. No slip means that you have boundary layer. Okay, so this is okay. Then you have this interior. Also, you need to touch this one. This is related to the cells. Okay, with this one you don't need to modify anything there. So we set up the boundary conditions. As you see, this is very important, boundary conditions. You don't give these values or you don't give the inlet velocity, nothing will happen. Okay. These options, you need to touch anything here. No, no. Reference values. This is important. These are the reference values used to compute coefficients. So here you can compute forces, but also you can compute coefficients. So we want to compute coefficient, you need to give your reference values. So the inlet velocity, okay, so here it was 90, you need to give reference viscosity, all those reference quantities, okay? So our reference area is 1. Attention, is area. So you use the core times the depth. When you work into D, it is a unit depth, okay? So it is 1. This is okay. Here, nothing. Here, nothing. Now we move to solution, okay? So here we define the problem, okay? Now we move to solution, and this is the solution method. So here, I hope you have seen, I think you have seen some numerics. So these are the methods used to resolve the Navier-Stokes equation. When it comes to methods, there are many methods implemented in Fluent. So here I'm not going to detail about the theory. I just want to let you know that use the default values. Okay, so you click here. What is Fluent proposing here? It is very robust. Okay, so this is a very good method. Use this method. Okay, but there is a lot of theory behind this. In controls as well, use default values, okay, what Fluent is proposing. Now you go report definition, okay, so remember that you need to monitor quantities. You need to compute CD, CL, mass flow, whatever. So here's where you define that. So as you right click here, you now go new and see that you can here create many monitors, okay. So we want to create 2 monitors for the drag, lift. If you want, you can also create it for the moment. Okay, so let's create a monitor for drag. You select the walls, so we want to monitor forces in these 2 walls. Okay, you want to monitor drag coefficient, that would be normalized using these reference values. You give it a name here, and then you want to report to a file. You want to plot, but also you want to print the value here in the console. Okay, so select all those options. And this is very important. Here you give the force vector. So remember, in our case, we're choosing that the velocity is horizontal. So remember that drag and lift are parallel and perpendicular to the incoming flow. But instead, if you choose to change the incoming velocity, you will need to rotate this vector in such a way that it will be parallel and perpendicular to the angle of the velocity entering the domain. Okay, so be careful. In our case that we're rotating the geometry, just leave it like this. We need to do that rotation. So you have CD. Now we create another monitor for lift. So you want lift coefficient. You want it here. Change the name. This is for vector is okay. Select these options. You are done. You have your monitor here. You expand that and you will have your report files. Okay, this is created automatically here. Okay, then here in monitors you have residuals, okay? There is a lot to talk about residuals. I don't want to enter into details, okay, because this can create confusion. But for the moment, we're going to run a steady. We're going to use a steady solvers in a physics that we are not going to have massive flow separation, so there are no unsteadiness. So these default values are okay. So leave it like that, okay? But this is the actual criterion for convergence, okay? So, but not necessarily you need to reach this criterion, okay? If you don't reach this criterion, doesn't mean that it's not converging, okay? It's just telling you that maybe you have a strong unsteadiness. So these monitors, leave it as they are. Then here, nothing to do. Initialization, very important. You need to initialize the solution, okay? This is a initial condition, boundary condition problem, Navier-Stokes equations. So besides the boundary conditions, you need to give also initial conditions. So as you go here, standard initialization, you need to define the initial value, and then from that value, you are going to start to iterate, okay? It is clear that the closest this value is to the final solution, the faster the convergence will be. But we don't know a priori that solution, but we can give something close to what we think will be. So it is a obvious solution that the velocity needs to be, we can use as initial velocity, the velocity in the inlet. So we give those values. Using these values, we can compute all these quantities. So you can give it manually, or you can come here, compute from, and you say that I want to use the values in the inlet to initialize everything, and automatically will compute this value. So see that this is reference pressure again, okay? It's relative to the operating pressure that you find in there. Velocity in the whole domain, and these two quantities are related to the turbulence model, computed automatically by Fluent, okay? So we're happy with this. We go initialize, and now we have the initial conditions, okay? So at this point, we're ready to run. Before running here in the canvas, okay, so you see here that you can zoom in, zoom out, but here also you can control translate, zoom in, you can control everything. You have many options here. Okay. Also, if you want to save this image, here you can copy this to the screenshot, to the clipboard, and then paste it in whatever you're using. Or you can save also the image, this image. You can go here, file, save picture. Okay, so choose the format, the location, whatever. Okay, so that was just before running. Now that we can run, you go here, run calculation, and here we set up, okay, the parameters to run. So the only thing that we need to change here is the number of iterations that we want to run. So the solver will run until it reaches the convergence criteria, or until it reaches the maximum number of iterations, whatever arrives first. Okay, so let's put here in a small number. We don't need to run a lot of iterations, so put here 300. Okay, and now we're ready to run. So you press calculate, and then it will start to crunch number Fluent. Okay, so see that you see here your monitors, CD, CL, and your residuals. Okay, if you want to stop the simulation at any point, you stop here. Okay, you press there. So let me show you. Stop. Well, actually, I arrived to convergence. Okay, very fast. Okay, so let me do something again. Let me initialize again, because I want to start. I want to show you something, and then go calculate. Okay, so if you initialize, you are restarting from 0. If you stop and press again calculate, you are starting from the latest state. Okay, so I see that it's running, but now it was very fast. Okay, actually in less than 60 iterations I arrived to convergence. By the way, if you run this exactly the same airfoil using a panel method, and you put a lot of panels, you will see that actually it's slower than the CFD. Okay, so CFD methods can be faster than panel methods. You see that here 56 iterations, it converged, it arrived to that criterion that we gave. But then what is important, that you need to trust these monitors always, okay? Because it might happen that your quantities that you are monitoring, in this case the forces, are still oscillating. So see here that you have CD. Okay, so CD is kind of flat, but we look at CL also, yeah, it's kind of flat. So maybe, yeah, we can say that it have reached converging because these are not oscillating anymore. But for instance, you stop the simulation here at iteration, let's say 25, still these are oscillating. So you have to be careful. You need to let the simulation run for a long time so you are sure that quantities that you are monitoring, usually integral quantities, forces, or heat flux, are not oscillating anymore. Okay, so let's say, for instance, that I want to run for longer time. So what I can do is that I can disable the residual control, or where I can reduce the tolerance. So as you go back here, is you want to disable this one, uncheck this. Okay, so you are not monitoring anymore, you are running until reaching the maximum number of iterations. Or is you want to reduce this, usually you reduce continuity, which is related to pressure. And let's put 0.5 there. Okay, so now we have a new value. As I press calculate, see that calculate doesn't start from 0, it will start from this iteration. Okay, so here you should use for this calculation only. Okay, it's okay, and see that from whatever you stop, it is starting, and now it reached the new convergence criterion. Okay, and it will stop. Okay, so this probably is better, and see that now you have the values there. Okay, we can compare, and this is interesting. Let's compare this with airfoil, but before doing that one, now let's see the color. So we have gone from here, solution, and now here the results. So usually people likes to see colors. So as you go here into contours, double click, and as you press save display, here you have this zoom in, and these are your pressure distribution, velocity distribution, and as you zoom in, see that we're here, you have the boundary layer, everything. Okay, and in here, in this wall here, remember that this is a wall, but we disable boundary layer. So see that this gives you much information than a potential solver. Okay, and funny, it can be faster than potential solvers also, that panel methods using a lot of panels. So here you can explore the quantities, but for our purposes, we're just interested in pressure and velocity. Okay, then also we can plot in the airfoil surface. So you go here, you see that you have plots, XY plot, and as you go here, you select, I want to plot the pressure, okay, in the airfoil, and see that you have, if you compare with airfoil, you're going to have those values. So you can also save this data. Okay, write to a file, or you can save this plot. Okay, for instance, this is the pressure, but if you want to plot the pressure coefficient, you have it here. Remember, it is normalized using this value, so it's important to choose the right values. Now you have it here. Okay, so incompressible, okay, the maximum pressure is 1. Okay, you have it here. And the other quantity that we want to monitor here is, you go to turbulence, you're going to have wall Y plus. So as you plot this one, so remember that we did this estimation. So see this 60 and the value we put. See that we have something about 60. Okay, so this is okay. So it means that we're using now that model that we were targeting to. Something important, that is impossible to have a continuous value of Y plus. The Y plus depends on the wall shear stresses. Wall shear stresses are not constant. Okay, so but in average, you should look at this quantity, and you should see that they are kind of within the limits that the values that you chose. So see that we were targeting something that higher than 30. So you see that most of the airfoil is higher than 30, so it is okay. So we are here using a model to resolve the boundary layer. If your Y plus is closer to 1, you are resolving the boundary layer. Later we're going to see that. So this is it. This is a simulation, how you run. So as you see, it's very complex. There's a lot to do to set up a case, but as soon as you you understand the workflow, everything is automatic. If I go back to the workflow, see here that now you have more files. So now you have the solution file. Remember also to save every now and then. So now you have solution file of Ansys, case setup, but also you're going to have these files, CLCD. Here you have the output of lift and drag. Okay, so there you have the location. So if you go here, you have all that information. You also have it in the screen now, but if you want then to plot this information, you have it there. So you see that in Fluent, you have it here reporting on the screen. Then also you have the text file with that information. Always control here because it's telling you all the files that are being saved. So let's do now something. Let's compare Fluent with airfoil. Okay. So let me go, and this is what I'm asking to you in the exercise. Now the same airfoil that you use, run in Fluent, and let's see how far or how close you are. I'm not expecting to have the same value, by the way, but something close. So let me run 0012. I go upper, bis, Reynolds was 6 million. So see here that we don't need to give velocity, nothing. Only the Reynolds number and then give a solution. CFD, you need to give a lot of information. And now let me increase iterations. 100, and let me go alpha 0, but we're running alpha 4 if I will recall, and this is what we have. So we have CL and CD. So CL 0.44, so see here that is about there, okay, and then CD 0.00593. So here we see that we have a large difference, okay, but remember that airfoil, it computes transition, okay? So see that it's telling you that you have transition to turbulence and about this distance, and this can have a large influence on your solution. Instead, when it comes to turbulence, there is a lot of theory, okay? And usually the turbulence models, it takes the boundary layer is fully turbulent. So you can imagine that we have that mismatch due to that. So if I change now the parameters, the transition in airfoil, probably I will get closer to CD because now I will try to set the transition to turbulence. So let's do that. Okay, so as you go to BPAR, we change this one. Okay, set turbulence here and here. So now I will trip the turbulence at the beginning, and let me run again. So see that now CD increased, and see that now it's getting closer. So see that having that solving or resolving the transition or having a fully turbulent boundary layer, it changes a lot the coefficient CD in particular. Okay, CL is not a problem, CD is difficult to compute. Okay, so usually we know 2 pi will be CL into D, then we have the correction for wind. So computing CL in general is easy. CD is very tricky, and there is this strong dependence in the transition to turbulence, and this is very important. Okay, CFD data tends to correlate better, okay, when you have a fully turbulent boundary layer. Okay, and let me go here. I would share with you these papers also. Okay, and this is a very interesting article. Okay, and I invite you to reproduce these results. Okay, so it's a critical assessment of wind tunnel results for the NACA 0012. So we have a lot of experimental data, but as we read this paper, we are going to arrive to this plot. Very interesting plot. So see that what you have here is you have different experimental data, okay, but in some of this experiment here is natural transition. Okay, you have the reference here, and here you have forced transition. You are tripping the transition to turbulence, and see that there is a large difference between CD computed. Even in experiments, you have that transition. Okay, and as I mentioned, that CFD data tends to correlate better with experimental results where you are forcing transition. So as you look at here at the Reynolds, okay, 6 million or whatever you are using, and then you compare, you will see that you will fit better with this curve. Okay, this is very important. As you are comparing with experimental results, you need to see what kind of data you are getting. If you are getting natural transition or forced transition. So for instance, let me show you something. I suppose this one. So I will share this paper, very interesting. And here, this is another one that you have a lot of data, and see here that when you go here, you see that it's telling you that this case is free transition. Then you are going to have forced transition. Okay, you have agreed that it's forcing transition. They are giving you the Reynolds number, also the Mach number, if you have compressibility effect. So it's always important to check the data that you are getting, because it happens very often, okay, that you are doing validation and you are comparing with experiment data, but probably that experimental data is natural transition and your coefficients are way off. You saw here that it was 2 times now smaller using natural transition. So it's very important to check that data. As I mentioned, there are many turbulence models. Okay, so even in CFD you have transition models. Okay, so see here that you can enable transition models, and each model will give you different values. Okay, so this is a complete semester in theory how to deal with that, but the recipient giving you, it will work, okay, with no problem for these cases. So that being said, okay, at this point I think we can now compare with airfoil. Okay, so let's rerun this case. Okay, we run at 4 degrees. Now let's run this same case. Okay, let me close now, but let's run at 0 degrees. Okay, so went there, let me save. So this case, it was 4 degrees. So let me go here, rename, put here 4 degrees. Okay, so you have the file here. So as I say, I will ask you to run at least 3 angles of attack. Okay, so try to do, for instance, 0, 6 degrees, and 10 degrees. Do not go to the stall. Also, predicting a stall is very difficult. But if you are curious, go and try to do a stall. But usually stay in 0, 4, and 10. That will be okay. And compare with airfoil results. So this is 4 degrees. So I want to run now for 0 degrees. Okay, so what I can do is that I can modify the angle here and rerun everything, but I want to clone this one. Okay, so you select everything, you go here, duplicate, then you're going to duplicate this case. All this setup, it is exactly the same. Okay, you don't need to change anything. The only thing that you're going to need to change, it is the angle here. So let me go here, let me rerun 0 deg. Okay, if I open here, so see that now you have the new files there. Let's open here. I will change only the angle here. Okay, I will put here 0 and go generate. See that is 0 degrees. We're happy with that. Save every now and then. Whoops, no, it's here. Here. So see that here it's telling you that you need to open, because this passing automatically. You just right click and refresh. So when you refresh, it's just taking the geometry, generate the mesh with the parameters that you know are okay. And then it will transfer the solution to Fluent. In Fluent, you have exactly the same setup. You just need to go there and click run. That's all. So as you see, very handy now to parameterize. There are more clever ways to parameterize. Okay, so here we're duplicating, but also you can create a table and you can link the table to the case. So you don't need to replicate this, but that is another subject related to optimization, designers experiments. For your small simulations, it's okay to work in this way. Now duplicate the 3 cases and you are going to have all the information is going to be saved in different folders, by the way. Okay, so it's doing the mesh. Let's wait a little bit. Okay, see, the mesh is done. So I forgot, when you have the lighting, you need update. So now we update here. So first it created the mesh. Now update, transfer the mesh. Okay, so it's transferring the mesh to Fluent. So when you see the green check mark, it means that it is okay. it is okay. And now here in theory, you can go right click and refresh, and it will do everything automatically. What we want to open Fluent to see what is going on, okay? So as you save here, see here that now you have more folders now. Previously Flu1, that you have the new case. So let's double click here, yes, and let's launch. Let's start. Okay, so now we have the new mesh, so see that automatically the angle, everything, the setup is exactly the same. At this point, we're ready to run. You don't need to change anything. Okay, if you want, you can change something, but you don't need to. Press calculate, it will do the initialization. Okay, so it will tell you, okay, you need to initialize, but it's using the default values that we set up previously. And now it's running, but now let's compare. Okay, these results at 0 degrees with airfoil 0 degrees, but we're interested in CD. Okay, CL, we know that it has to be a value close to 0. So you look here, you see that CL is not properly 0, but it's a small value. But CD is interesting one. So see that we have 0.008. So let's compare with airfoil at 0 degrees. So let me go upper BPAR. So I want to change XTR. Okay, I want to put it to the default value, and let me run alpha 0 degrees. So see, this is the value using natural transition. So see that it's 0.005, much lower than this one. But remember, airfoil here is computing natural transition. So if you want to force transition, okay, you go back here, XTR and BPAR, and let's put this value to force transition, and you go alpha 0. So look at CD, okay, and see that now it's going to alpha 0. See that now increase. Why? Because the whole boundary layer is turbulent, shear stresses the wall are larger. It's obvious that it's larger. So if you compare now with the CD of the CFD simulation, see that the values are closer. So what it was telling you, okay, CFD data tends to correlate better with fully turbulent data. Be careful, okay? So I just wanted to show you that. Okay, so this is it. Again, you go here into graphics, contour, you will have this for pressure. You can plot velocity. Also, you can go here and plot the XY plot. Okay, so you select the pressure suction side. So this is symmetric, so you have this behavior, and you can check also turbulence. Okay, the Y plus is the one that we're interested for the moment. So these are values okay to what we were just aiming. So this is it. Okay, this is how you do the simulation. You have the recipe to run your airfoil compare. So something important, I'm not expecting to have a perfect match with airfoil, but the value should be close. Okay, close. Now it's 0.35, 0.32, okay, but I'm not expecting perfect match, but I want I want you just to get the feeling of CFD simulations, just to see, you will see that it's much more complicated, and also to know that you have this tab here, turbulence, and turbulence is extremely important. It is what is going to change everything in your simulation. Okay, so there is a lot of theory behind that. So now that you have that, okay, so you will run 3 cases. So what you can do now with this is just clone this one and run, for instance, 10 degrees. Okay, so you can visualize the flow, if there is separation and everything. Okay, so this is your recipe. Okay, it is again, it is more complex that I'm showing you, but this is enough to do the comparison for your assignment, your source assignment. So thank you for attention, and see you next video. Bye.